Great. We are now live on the third meeting of the seminar on Intuitionism and Constructive Mathematics. And today we have quite a task. We are going to digest Brouwer's 1927 paper on the domains and definitions of functions, in which he proves the uniform continuity theorem, that if you have a full function on the unit interval, that's a function defined everywhere on the closed interval from 0 to 1, then it's uniformly continuous. And we will spend quite some time digesting what he has to say, trying to piece apart what the argument is, how it comes about. And at the same time, we'll have a look at chapter 4 in Buchholtz and Van Dalen, and have that help us when we get stuck, so we can go back and forth. Okay, so I should probably say that this is the hardest reading of this seminar I think we'll assign. But we should also get some benefit from it. We'll learn much more about Brouwer's style than if we just read secondary sources. Any comments before we start? How did you find it? Anyone have something to say about that? There's some raised eyebrows. Okay. Let's take it from the beginning. So one thing that's very nice about this chapter from the source book of mathematical logic is that Charles Parsons gave an introduction and also collected with quotes Brouwer's definitions of all the concepts that are involved, because he assumes that we know the earlier papers in the Begründung series. Right? So it starts in 1918 and continues up until around this time. So many things he takes for granted that we have to know. And here we have, on these couple of pages before the article itself, we have all the definitions, so we can have a look at them and try to parse them. Okay. But maybe we should just start with section 1. So that's on page 457 of the book, of the excerpt. And I was wondering if maybe perhaps one of you would read aloud in the beginning. No?
Only looking at me.
Everybody else looked down. Okay, then I'll read a bit, and then we'll try to make sense of it, and then we can jump maybe ahead once we get the hang of it. Okay, so following section 5 of the Begründung number 1, we have these kappa intervals and lambda intervals in the naturally ordered species of finite binary fractions, right? So finite seems superfluous, but binary fractions we understand, right? So just a fraction of a natural number with a power of 2 in the denominator. And it's naturally ordered because we order them by the position on the real line, right? And there's a helpful definition of what they are. So a kappa interval is, say, of size n. It's a closed interval from a over 2 to the n to a plus 1 over 2 to the n for a an integer, and the lambda interval is the same, but it goes from a over 2 to the n to a plus 2 over 2 to the n. Okay, so I think Brouwer changed his mind a little bit over the time about how exactly to present the continuum, but the basic idea is the same. We use these choice sequences to pick a series of natural numbers, and then we assign to each such series something that presents either a rational number or a rational interval of decreasing size. All right, so in this paper, he uses binary fractional intervals, and they're required to, the lengths are required to go to 0 positively. Okay, so we have a modulus of convergence for these binary intervals. Okay, the next thing, a point of the linear continuum. So this is such an unlimited sequence, the generating intervals of the point, and they have to be strictly decreasing. Okay, Okay, so that's how he presents a point of the continuum. So let's perhaps go back and see his definition of a set. So he starts out calling it a set or a Menge, and then it becomes Spreidung, spread, as we say today. And it's a good thing that he invents a different word, because using set would be quite confusing for people confused to set theory. So let's try, when he says set, to read a spread instead, and we'll talk about spreads. Okay. Let's see, the definition is on page 453. So a spread, I'm going to read spread instead of set. A spread is a law on the basis of which, if repeated choices of arbitrary natural numbers are made, each of these choices either generate a definite sign series with or without termination of the process, or brings about the inhibition of the process together with the definitive annihilation of its results. Okay, so the way we're going to parse that today, start making some definitions on the board. So we have the first concept of a spread, and to make it clear that as we compare it to other notions of set in mathematics, we call these a naked spread. And basically, I'm also going to try to introduce some typing, because one thing that's confusing in these old works is they mix up finite sequences of numbers with numbers, and Booleans are just 0 and 1, the numbers. So if we try to introduce a little typing discipline, maybe that'll help keep things straight. So what he means is that it's a function from lists of natural numbers. So let's say list n to pool. And it's such that if something is allowed, then so if it sends a certain list to true, then there is some continuation of it, which is also allowed, right? So I'll use U to range over a list. And so let's call this thing S. So if S of U is true, then there exists number n such that S of, and I'm going to use the semi-modern notation. It's quite not how you'd write the SNOC or inverse cons in computer science, but this is very common in mathematical logic, as you probably know. So U tie n means you take the list U and you stick an n at the end of it. This has to be true too. Okay, and then it has to be downward closed. So for all U and B, if U is an initial segment of B, which I'm going to write like this, and V is in the spread, and then U is in the spread too. Hope I got that right. Make sense? So we picture it something like this as a tree. So here's the empty list. And let's say it's also inhabited. Let's put that in here. S of the empty list. It's true. If you require that it's just inhabited, that there's some list that's in there, then you also get the empty list in there from this axiom. Okay. So then a certain number of one-element lists are in the spread, and then a certain number of two-element lists, and so on. Okay. And then we imagine a process, an ongoing process of picking. So start at the root, then we pick one of its descendants. Then we pick a descendant of that. That might be a choice. So we picture this as an ongoing process that's never completed, but we can always extend it at any point in time. Yeah.
So Parsons' notion of spread presented here disagrees with this, where it says that the law where for every element in the spread, there's an additional concatenated element we can tack on to the end, and that also guarantees the spread. It says the process can terminate for some of these elements. So I'm looking on the second page of the document, so now.
Yeah.
Rule 4 for the notion of admissibility. And when I say second page, I mean the first 2 pages.
Okay.
I think at say that second node there on the left, you've got these 2 continuum things, but the rest of them, as he's written it, are still there, but they're the choices that are terminations. So like if those are 1 and 2, then choosing 3, you go to 3, but then you see the termination. So each, it says later, after every unterminated and uninhibited sequence of n-1 choices, at least one natural number can be specified that, if selected as the nth number, does not bring about the inhibition.
Okay.
Thanks. Yeah. So this is a singleton 0. This may be singleton, or the list containing just a 2. Then we might have an inhibited. I guess I should have used red for the inhibiteds, but let's now use orange. It's a warning sign. So it might be that this one is it's there in the set of all lists, but it's an inhibited one. It's not part of the spread. That's how I understand. Okay. So that's the notion of a naked spread. And then we can dress up a spread. And that's then what happens when he talks about getting continua. So a dressing of a spread is then something, you imagine a function that assigns to each node here, each list, a rational number or a dyadic interval or something like that, and with then some further specified restrictions. Let's see where we are. Okay. So we get a point set of the continuum if we take such a dressed spread where we pick decreasing sequences of dyadic rationals for each list in this one. Okay. The next thing is the species of points of the linear continuum that coincide with a certain point, and that's what he calls a point core. Make sense? So we can now talk about if we have such a point set, a point spread, so a dressed spread that gives points of the continuum, we can talk about the species of elements which give coinciding points. Okay, that makes sense. It's a point core. Okay. And then we get to the unit continuum, and he says those are those point sets where we only use intervals covering the unit interval. Makes sense. That way they represent elements of the unit interval. Great. So then comes a quite difficult paragraph from Begründung 2 about the species of intercalation elements. And this is a little bit of extra generality that he had introduced for how to generate point sets of things that are not metric spaces. So we don't really have to care so much about this because we're just interested in the continuum. But we can have a look at, if you look at the excerpt on page 456, the left paragraph, there's the definition of these intercalation partitions. And he does this for, you start with M at innumerably infinite. And we can also have a look, if you want, we can look back at the definition of cardinalities. But basically, you take an infinite ordered species that's everywhere dense in the strict sense. So it could be, for instance, the rational numbers. And that would be another way to generate the continuum without using the absolute magnitude of the intervals. So you don't have to, you just say you have to pick pig interval such that eventually everything but at most one of the rationals are excluded. And it's a kind of a mixture between a Cauchy and a Dedekind way of specifying numbers. So it's not so relevant to understand the rest of this paper. We can make do with point sets defined using the binary intervals. Okay. So this is what happens the next paragraph. So now we are this third paragraph on page 458, where we.
One question about it. So you said this is a mixture between Cauchy and Dedekind.
Yeah.
So constructively, those are distinct, right?
Yeah, but it's not. I mean, I don't mean that it really is the Dedekind, but it's.
Is it different from both of them?
It's not really different from the Cauchy perspective, but it's a way of talking about Cauchy sequences of intervals in a way that looks like it pays homage to Dedekind, right? Because, okay, let's have a look at what it actually says. So now we are in the left paragraph, on the left column on page 456, where we have these intercalation partitions. So we generate in M, so say the rational numbers, by an unlimited sequence of free choices, a left and a right subspecies, an arbitrary element of the left subspecies preceding an arbitrary element of the right one. So you have two different sequences. Everything in the left has to be left of everything in the right, right?
Yeah.
So that's sort of like a Dedekind cut, but instead of having a whole set, you just have the sequences. You have two sequences that are like the conditions for the two sets of a Dedekind cut. That's why I said it reminded a bit of the Dedekind definition.
Okay.
Even though it's still based on sequences, so it's okay. Okay, now back to the main text. Yeah, so he says that we get a similarity correspondence, and that's an order-preserving bijection between now this binary interval notion of the unit interval with the K of M, which was this thing we got from the 25A paper, the continuum over M. So that's just this comment that you can go back and forth between those two presentations of the unit continuum. Everybody with us so far? Okay. Okay, so now we get to the notion of a real function. Okay, so this is quite uninterpreted here. It's just a law that with each of certain point cores of the unit continuum, which will be denoted by the letter xi, and form the domain of definition, one associates one point core of the linear continuum, which will be denoted by the function value eta f of xi. Okay, so it's just a law without specifying further what a law means here. Except we know that it has to be extensional because it has to be a law relating point cores to point cores, and a point core was the species of all the different sequences that gave the coinciding real numbers. It's a little harder to slip between, in the intuitionistic sense, there's never really a real number. There's the spread, and there's these going concerns of ongoing developments of sequences, but they're never completed, right? But we can still think about what it would mean for two such processes to give coinciding numbers. And similarly, we can talk about orderings. We know that in a point set of the continuum, if one process, there will be a time when one process will generate a point definitely to the right of another point, because we could make the interval so small that they will not overlap anymore. And then they will never overlap, and we have okay?
The translation is kind of bad. It's very hard to understand this sentence, which is a full paragraph. By real function or short function, we understand the law of that, and then let's leave out that with each of certain point cores. Associates one point core?
Yeah.
Is that the idea?
Yeah.
It's just the wrong preposition of the word. It should be true. Each of certain point cores, each of certain ones associates one.
Yeah, we can see that the translation is by Stefan Bauer-Mengelberg, and maybe his English was probably his second language, and German his first language.
Yeah, that's So the idea is we have certain point cores. Not all of them will be in the domain,
That's right.
but for certain of them, to each one of those, we associate one point core.
Yes.
That's the one.
It's a one-valued function.
Single value.
Yeah, single value.
So does he talk about the notion of equality on these point cores at all?
Yes, because we had the notion of coincidence and the definition of a point core.
But that was only this indirect reference, right?
Yeah. Yeah, I think he would take it as a further step to say that point cores are form a partition. That either they are disjoint or they are identical. I think that's an argument you can make based on his definitions. Not that you can hide either way, but if...
The question is there such a notion that's central to this definition?
Yeah, I think we would be able to prove, at least if we try to formalize what notions of inference he would allow, that if two point cores intersect, that is, if we have a sequence in intersection, then they are identical. Then every sequence in one is in the other, and everything in the other is in the first. That we probably have by transitivity of equality, basically.
Using equality of subsets.
Yeah. Yeah. And equality of sets, or of species rather, is defined earlier as extensional equality. Okay. So we have the definition of a continuous function, and he gives the definitions of negative and positive continuity at a point, or at a point core. So, and that's the what we would expect. And I think for negative continuity today, we would translate it with a double negation. And the positive one, we would have to have a modulus of convergence. Okay. So now the first theorem, which already appeared, I guess, in the first of the Begründung papers, 1918, says that every full function is negatively continuous. So means that for every fundamental sequence, so a fundamental sequence here, that's important. For Brouwer, a fundamental sequence is a law-like thing. It's not a choice. It's an actual law-like thing. So we have a law-like sequence of point cores positively converging. That means we have the modulus of convergence, and then we get, so that's the positive convergence of a law-like sequence. Okay. Then if we have such a thing, then the function's values will be negatively convergent. And the proof here is quite easy on this conception. But maybe I think we'll skip it for now to make sure we have time enough to talk about the other elements. So let's jump to section 2 and 3. So he says at the end, after the proof, so this is an immediate consequence of the point of view. It's been mentioned by me in lectures and conversations, and suggests the conjecture that theorem 3 below is valid. So we look to the end. Theorem 3 is the last line of the paper. Every full function is uniformly continuous. So that's what we're going for here. So now comes the main point, which is leading up to this proof. Okay. So let's start on section 2. We take an arbitrary spread. Okay, so we read spread for set, and let mu be a denumerably infinite set of finite inhibited or uninhibited choice sequences upon which M is based. Yes.
You're skipping Theorem One, is that right?
Yeah.
Did anyone kind of browse the proof and give like a summary of what makes it true? Because it seems to be kind of a warm-up for the theorem we're going for, right? What makes them more clear?
Okay, let's go. Let's have a look at it.
Just because it's very similar to the theorem we're shooting for, it's just negative continuity rather than
Yeah, the conclusions are.
continuity. And
Yeah.
Why is this one already?
Okay.
I didn't read the.
Yeah.
I
So
readily admit I didn't prepare. So
okay.
maybe just-
Now let's do it then.
But I think it'd be helpful to understand it.
So Steve wants us to talk about the proof of Theorem One. So we'll do that. And so we're proving a negative statement. So we're allowed to reason by, we assume that we have discontinuity, and then we derive a contradiction. Okay. So we have the fundamental sequence of point cores that converge positively to psi naught. And we assume negative discontinuity. So we assume we have a natural number p and a strictly increasing sequence of natural numbers p1, p2, and so on, such that the distance between f of psi p nu and f of psi naught is greater than 1 over p for all nu. Okay, now we define a new point core, psi sub omega, and we start using the generating intervals of a point belonging to psi naught. Okay, so we have psi naught, so we have a process that generates intervals converging around the point represented by psi naught. Okay, so we start picking those intervals. So we're defining a choice sequence here. Okay. Let's see, where are we? So temporarily, we pick for every natural number n, the first n intervals of wow1. So here, wow1 is the sequence of generating intervals of the point belonging to psi naught. So this Greek letter is, yeah, that's called wow, or the letter itself is called digamma. It's an archaic Greek letter that he picks here. Okay. Good. But we reserve the right to determine at any time after the first second up to the mth interval have been chosen the choice of all further intervals in such a way that either a point belonging to psi naught or one belonging to a certain psi p nu is generated. Okay, so at some point we may decide to switch to the intervals from psi p nu. Okay.
Yeah. So now we have to use somehow the fact that this thing is defined there. We can use that.
Yeah, that's eventually what brings about the contradiction. Okay, because we say then the function f, he writes f of x, but he means just the function, is not defined for the point core psi omega containing this choice sequence wow2. So we have to argue that. Here he just finishes up and says this is this leads to a contradiction. So we have to imagine here how could, so now we get a little, yeah, it's good that it comes up. It gives us some insight into what he means by a law that associate point cores with point cores. So a function on the reals, right?
Yeah.
And the idea is that it has to, when it gives out a certain interval, I think we have the idea that it must use only a finite amount of the data that's been generated so far. We have these choice sequences that are the going concerns, the ongoing processes. And so we start producing intervals for psi naught. Okay. Eventually, either we will the function will decide, okay, now we're we're going to output one of the approximating intervals for f of psi naught. Okay? But we could also have switched, because we have this option of switching because of the convergence, the positive convergence.
Yeah,
Then we have the option of switching to the intervals for the approximating sequence, the fundamental sequence of the point.
Yeah.
Okay, but the function can't take that into account, right? Because it has to be extensional, and eventually we have the sequence, the p sequence that gives the subsequence of the fundamental sequence that stays 1 over p away from the image of the of psi naught, and that's why this function, it cannot be defined at psi nu. Okay, so that's the argument. So it's a little bit sketchy here, because I guess he's a sketchy here because he gives a proof of a stronger statement. So that's why he's okay. It's second nature for him, this kind of argument at this point. But we'll have a look at the more thorough argument for the stronger claim, theorem 3. Okay.
I mean, we start with a rule that assigns to some arguments
Yeah.
their values, and then the question is this rule total on all the arguments? Is it defined everywhere? There's some tension between the continuity condition and being defined everywhere.
Yes.
Based on those often.
That's right. And since he's just aiming for a contradiction here, it's not so bad. All right. So now we have this mu, which presents a spread. And we let a natural number beta be associated with each element of M. So what he's saying here, suppose we have a function from M to the natural numbers. And what he's going for here is a kind of continuity principle. If you read in Scholz and von Dahlen, there's this continuity for numbers, which plays a role here. So let me just put it up. We're now considering a function from a spread M to the numbers. Okay. Let's see what he says about such a function. There is distinguished in mu a removable numerable subset mu1 of uninhibited finite sequences, such that with an arbitrary element of mu1, the same natural number is associated for all elements issuing from mu1, while furthermore a proof H is given that makes it apparent for an arbitrary uninhibited element of mu that every uninhibited infinite choice sequence issuing from it possesses an initial segment belonging to mu1. So it's not exactly the clearest mathematical prose. Okay. Yeah. Yeah. So we'll talk a lot more about how these things present topologies. But say you have down here a sequence U, then we say that alpha is in mu if and only if mu is an initial segment of alpha. So by alpha, I think of an infinite choice sequence according to this spread. Okay. So what he really saying? He's saying we can decide based on a sequence whether we know enough information to output beta. And if we at some point know enough information, then all further finite sequences will give the same element beta to any alpha that is contained in sequence U. Right? And we have a proof of this. Okay, so let's. So what will be the main point of the following is analyzing these proofs H. Okay. So now we get a little more insight into what Brouwer thinks of as a function, such a function from M to the natural numbers. Uninhibited means that it's still in the spread, that we're still allowed to make further choices. It's not ruled out by the spread.
You have your M is a set and U is a set. Am I reading both those sets as spreads?
No.
Okay. So M is a spread, but U is a set.
Yeah, I think that's right.
Okay.
That's a reason why you try to keep using the spread for when you're using the spread, and not try. I mean, I could be wrong. I'm not claiming I have the complete understanding of this paper. Hopefully, we can figure it out together. But that's how I read it. That otherwise, I don't know how to make sense of this first paragraph. It's clear that M has to be a spread, but if we identify the spread with the sequences that it generates, then what would we need the mu for? Right. Okay. Anyway, so let's go to this thing that the decision with respect to the number to output according to the algorithm of the rule establishing the correspondence is not postponed to further choices. That's what I think. So at some point, you've made a decision for an initial segment, and everything that goes through that initial segment must give the same answer. Okay? And every sequence must pass through this set mu1 that tells you what the output will be. And furthermore, he says that mu1 has to be removable. So removable means that it's decidable inside mu whether a list is in mu1 or not. So actually, mu1 is what we later come to call the bar. Right? So let's think about what this mu1 is. So it's a removable subset of uninhibited choice sequences. So it has to be a subset of the spread that we can decide for a given list whether it belongs to mu1 or not. That's the first part. Such that with an arbitrary element of it, the same natural number is associated for all elements of the spread going through that. Right? So every choice sequence that goes through such a U in mu1 will be assigned the same natural number. Okay? While furthermore, a proof H is given that makes it apparent for an whose initial segment.
Okay, so I need initial segment up to one.
No, a choice sequence is the whole process, but a choice sequence that starts with U. Right? So if we have a particular, here's our U, and so the initial part of it is determined by U, but then it could be anything that's allowed, that's uninhibited further on. Okay, that's what he says. So if U is in mu1, let's say U is in mu1, that implies for all alpha in U, and let's call this function something called G, G of alpha equals, well, let's say there exists beta a number such that we get the same results, beta, for all alpha that goes through U. Okay? there's a lot going on in the sentence that where he defines basically what we call a bar. Then what do we know now? We know it's this decidable subset of the uninhibited sequences. We know that we get the same value for every choice sequence that goes through an element of mu1. And now comes the hard part. We need a proof H that makes it apparent that for an arbitrary uninhibited element, so an element in the spread, in the way I define a spread, that every choice sequence issuing from it possesses an initial segment belonging to mu1. Okay? So what this means is that any choice sequence in the spread has to pass through mu1 at some point. That is the barring property. So let's pick another color. Purple should be visible. Let's see. Green is not good on the blackboard. Let's try purple. So every uninhibited sequence, that is every element in the spread, must pass through this detachable set mu1. Okay, and we have a proof H of this fact.
So that he labels the proof, right?
Yeah.
Gives the proof name.
Yeah. Because later he will label the canonical form of this proof. Let's get to that.
So are we supposed to understand this proof as a syntactical object?
And that's a good point. So
I would assume not.
we will definitely not. I mean, we already know from the last paper the disdain he has for language and formalization. So it's almost clear that we should not understand this as a linguistic object. I did bring some other versions of the proof. This is Heiting's introduction to Intuitionism, where this is based on the similar proof of the Fan and the Brouwer theorem, proved in 1924. But here Heiting says a proof must be finite. So it could be, I mean, there's some argument, and you could try to correlate the various instances, but it's quite clear that such a thing would not work. You have to really allow it to be a mathematical object. So a proof is a mathematical object.
Okay.
Well, but he manipulates it, right? So it's a proof, but he does something with it.
He does something with it.
He
So
doesn't need that for Theorem One, right? It doesn't seem to
That's right.
require it,
Yeah. So that's why it's a very historically important thing to analyze. Exactly because of this looking inside the proof and see what's going on and manipulating it. Okay.
So one of the problems I always have with this is that you might work under the assumption that such a proof exists, but you might not have the exact form.
Yep.
Then what do you do? Because you can't analyze it because it's only an assumption. So when you come to things like when you start adding axioms that internalize these things, you have names for them, then it becomes problematic because you can't actually look at the structure. Right?
That's right. So somehow it's supposed to be apparent, given his conception of what a proof is, that it can be analyzed in normal form, in a canonical form, if you have it, even if you only have it hypothetically. But that should be enough because you're only going to use an implication eventually on a closed thing in a canonical form. So we can try to think about what the philosophy is, but of course it start to clash once we formalize things and axiomatize things. Then we would have to check that everything actually can be brought in canonical form. Good point.
Also, the word algorithm here in italics, what's going on there? Is it just italicized because it's a foreign word? Or is it?
It's a good possibility that algorithm is italicized because it's a foreign word. We know that algorithm was in use customarily in mathematical writing even before the 30s. As difficult as it might be to imagine that it was, it definitely was. And we know that Brouwer read a lot of descriptive set theory from the French semi-intuitionists or pre-intuitionists, Lebesgue, Borel, and so on. And Borel, in fact, had a definition of computable function on the reals, where he uses the words algorithm. So probably it's the same sense that Brouwer has in mind. Brouwer thinks of himself as continuing the tradition from Borel, but it's something if one wants to do some historical digging, one can try to find the relevant quotations among the French semi-intuitionists and try to figure out what they thought an algorithm was and whether that's what Brouwer thinks an algorithm is at this time. Okay. So now I'll go to page 460. If we say that an element of mu is secured when it either is inhibited or possesses a proper or improper segment belonging to mu1. So I suggest we kind of ignored what happens to the inhibited sequences, because in the way I formalize the spread there, we only talk about things that are uninhibited. But we could try to correlate the two notions. So let's say it's secured if it possesses a segment belonging to mu1. Okay. Then mu splits into a numerable set tau of secured and a numerable set sigma of unsecured finite sequences. And the proof H we were just talking about shows that an arbitrary f sub s is securable. That is, every infinite choice sequence that issues from it and is uninhibited for the spread possesses a certain segment belonging to mu1. Okay, and then there's a footnote. When carefully considered from the intuitionistic point of view, this securability is seen to be nothing but the property defined by the stipulation that it shall hold for every element of mu1 and for every inhibited element of mu, that it shall hold for an arbitrary f sub n1 through nr, so just a list basically, as soon as it is satisfied for every nu for the 1-point extension, this the tie of the list with nu. This remark immediately implies the well-ordering property for an arbitrary f sub a list. The proof carried out in the text for the latter property, however, seems to me to be of interest, nevertheless, on account of the propositions contained in its elaboration. Okay, so here he gives a different argument. He says, okay, basically, what I'm just arguing for a certain kind of well-orderedness property on the nodes of the tree, but I'm going to give you a different proof because I think it contains some interesting remarks. Do you understand this footnote? I mean, it's this upward induction of the tree here, where I draw the tree going downwards, that if you have something for all the immediate descendants, if you have a property that persists upwards, and he says if it's true at a bar, then it must be true at the root. So that's the argument there. Okay. So that seems like the easy argument, but he's going to make it harder. Yeah, so here we have to make it difficult. Okay, so we continue after this footnote 7. So now let H sub a list, so a particular list. So let's just read, instead of reading SN1 ... NR, I'm just going to say HU, because I'm using U as a variable for a list. Okay, it makes it a little easier syntactically. So let H sub U be a proof in which the securability of the element F sub U of sigma is derived. Then what this securability and this proof rest upon is, if we leave aside the fact that mu1 and the inhibited choice sequences of mu are given exclusively the relations, are given, it's a little hard to read here, the print was kind of weak. Exclusively, the relations obtaining between the elements of mu are formed by the composition of elementary relations, E of the kind obtaining between two elements, f sub v and f sub v one point extended with some n, of which one is an immediate extension of the other. Now, if the relations employed in any given proof can be decomposed into basic relations, its quote-unquote canonical form, that is, the one decomposed into elementary inferences, and let's postpone the footnote, it's an important footnote, we'll just postpone it a minute, employs only basic relations. In the case of the canonical form K sub u of the proof H sub u, we can therefore ultimately infer the securability of F sub u exclusively from a combination of the species S sub u formed from the elementary relations E connecting F sub u to F sub an immediate ascendant of u and to the F sub u immediately extended with something with a property previously derived from arbitrary elementary relations E, and also from the fact that mu1 and the inhibited choice sequences are given, period. All right, so this is quite a mouthful. What do we make of it?
He's reasoning now about the structure of H sub u.
That's right, he's reasoning about the structure of a proof. And he says, okay, it might go from some relations between the nodes that we have when we have one is a subsequence of another, and we decompose these relations into the immediate steps up and down in the tree. Right, so immediately to one step up or steps down. Okay. Let me have a sip of coffee. Definitely be necessary to make sense of this. All right, so let's try to attack this footnote 8, which is quite crucial. So here we have to understand his notion of a well-ordered species. So that's what we get to here. Just as in general, well-ordered species are produced by means of the two generating operations from primitive species. So we could go back, but let me just remind you what the upshot is. So for Brouwer, a well-ordered species, so it's an ordered set, which is then, he says, they're generated inductively by two processes from singleton sets, which he considered well-ordered. So you can either take a finite list of well-ordered sets and put them one after another. That's the first generating operation. Or you can take a fundamental sequence of well-ordered sets, so a law-like sequence of well-ordered sets, and put them all one after another. So suppose they're disjoint, then you just order them, everything to the left is less than everything to the right. Okay, that's the second generating operation for Brouwer's well-ordered species. Okay. Okay, now we understand his well-ordered species. So just as these are produced by two generating operations from primitive species, so in particular mathematical proofs are produced by means of the two generating operations from null elements and elementary inferences that are immediately given in intuition, albeit subject to the restriction that there always occurs a last elementary inference. These mental mathematical proofs that in general contain infinitely many terms must not be confused with their linguistic accompaniments, which are finite and necessarily inadequate, hence do not belong to mathematics. Okay, so that answers pretty definitively how he thinks of a mathematical proof here. Okay. It's not a finite linguistic thing. It's a well-ordered tree of inferences generated in the same way he generates his well-ordered species. The second paragraph in this footnote is also of interest. The preceding remark contains my main argument against the claims of Hilbert's metamathematics. A second argument is that the way in which Hilbert seeks to settle the question, which, incidentally was taken over from Intuitionism. So there's a little posturing there. Of the reliability of the principle of excluded middle is a vicious circle. For if we wish to provide a foundation for the correctness of this principle by means of the proof of its consistency, this implicitly presupposes the principle of the reciprocity of the complementary species and hence the principle of excluded middle itself. And I'm not able to really parse what this argument amounts to. Did you have any luck?
Is it like because it's consistent, it can't be false, so it has to be true? That's the presupposition. Something like that. I mean, I don't really understand what he's saying exactly, but like if the excluded middle can't be false, then it has to be true. That argument presupposes the excluded middle.
I think that's part of it. I think it's also part of it that it's not enough to look at a linguistic formalization of uses of excluded middle. I think part of it is also this idea that it's not enough to know that something is consistent for it to be true. And maybe he mixes those two arguments together to get this paragraph out of it. But I'm not able to really pinpoint it. I found it quite inscrutable. Anyway, it's of interest if you want to understand the few places where Brouwer actually says something about Hilbert. Otherwise, he was quite shy of directly naming names or something like that.
Well, Parsons gives us some hint, right? He cites this other thing from that. Equivalent to the principles of sort of third of reciprocity of complementarity. What's that mean, reciprocity? Mentioned here, Marx expertly making recognized as non-existent. In fact, as we also shown the ability of these two principles cannot be essentially different. It kind of seems to take me back.
Yeah.
Is reciprocity and complementarity like the litigation elimination?
I think so. I think not what they say.
Well, that sounds right. Yes.
Yeah.
So now he's saying that actually the fields are different. So maybe he's kind of withdrawing the statement.
That could be. Part of
I
the
just feel better about not quite understanding.
Yeah. Part of what's going on there is his insistence that he invented the distinction between mathematics and metamathematics. And he told Hilbert about this when they were both vacationing at the beach at the North Sea in around 1918. And he never felt he got sufficient credit for that. There's some sources I can point you to where this is discussed. Okay, but it's not relevant for the discussion right now. It's just interesting that it's here in this otherwise quite important footnote that lists down what is a mathematical proof for Brouwer. That is this mental construct that could be an infinite tree with infinitely many terms, but somehow it's not. But it consists of these fundamental sequences, so it's law-like. It's not. You can't make a proof by using choice sequences, right? Okay. So that's part of why we can study it and find a canonical form. Okay, so let's continue after. So now we go back to the main text, and we have these elementary relations. And for the last step of K sub u, so the canonical proof, we must therefore previously have established the securability either of the list we get by chopping off the last element, or of all the direct descendants. So this is now what he formalizes in the next paragraph. If we now call the derivation of the securability of an fu from that of an f restricted by 1, so take off the last element, a zeta inference, and the derivation of the securability of a list fu from that of all of its immediate descendants, a wow inference, then the proof K sub u forms a well-ordered species in which every full element is formed by an elementary inference that in case it constitutes the derivation of the securability of an element of sigma, represents either a wow or a zeta inference. So he says we can analyze this proof H into a canonical form K that's a well-founded tree where the an inner node that has a child either has a single child, in which case it's a zeta inference, and it goes from securability further up to securability of the immediate descendant, or it's a wow inference. I guess just a mnemonic that wow is kind of appropriate because this has one that had infinitely many premises, right? So a wow inference is the one that has infinitely many premises and goes from all the possibly infinitely many direct descendants to the node just above it. Okay, and the leaves of this tree are where we are immediately secured.
Ulrik, so I found that the reciprocity of complementarity thing is in the Cambridge lectures. So it is the double negation elimination, but only for species membership.
Okay, thanks.
A bit off topic, but how do you get wow from digamma? Do you know where that came about?
It's because in Phoenician it represents the phoneme W.
I see.
And then it came into Old Greek, and then the Greeks abandoned it. But then they used the, I think, no, I think the Greeks also used it for the letter 6, or for the number 6. But I don't know what that's not here nor there. But I mean, I guess it explains why we still have it, you know, even though it didn't go completely out of use because it was used as a numeral. But if you really want to know about the history of the Greek alphabet, I'm not the best source. I just know a little bit.
There's good Wikipedia resources on the
yeah, probably.
letters.
Yeah, we'll refer to the Wikipedia. Okay.
So, but the proofs are definitely mathematical objects, right?
Yes.
There's no way around that.
There's no way around that.
So how is he not? How is he an anti-formalist? I guess because mathematical objects are informal, it's just any other mathematical object.
That's right.
A mental construction.
Yes. Every mathematical object is a mental construction, including the proofs.
But so would you consider this meta-mathematical? Because he's the one who introduced the distinction between mathematical and meta-mathematical.
That's right.
So is this proof, even though the conclusion is purely mathematical, is this a meta-mathematical proof?
I think he would say that. I think we're thinking about mathematics and thus doing meta-mathematics. But for Brouwer, meta-mathematics is part of mathematics because it also studies a subclass of mathematical objects, namely proofs.
So meta-mathematical.
So the proof is the first class mathematical object itself, kind of mathematical, but it still only kind of exists in your head in your cabin in the woods.
That's right. You wouldn't be able to write it down because it's some infinite tree that every linguistic representation is inadequate, necessarily inadequate.
So it's a
conception. Sorry, it's a different conception than Ulrik's.
Much different, and a cause of much of their misunderstanding. Yeah.
So if it's infinite, I wonder if there's some co-inductive interpretation.
Oh yeah. So there are definitely co-inductive presentations of the Brouwer and Fan theorems, and even recently, I think there are computer science literature that connects up with this. Yeah, we can try. I don't remember the references right now, but we can find some. Yeah, probably also. And I think there are also some British people who are doing this. Okay, let's see what he wants to go with it now. We now assert that every element f sub u, and I can't read, but it must be of mu, of sigma, okay, possesses the well-ordering property, that is that the subset mu of m, I guess that's a subspread determined by fu, so those elements that necessarily pass through u, splits into a species of subsets ma that is similar to the species of the full elements of a well-ordered species tu each of these subsets being determined by a finite initial segment f alpha of choices that contains, I guess, of choices that contain fu and belong to mu1. Okay. So that's difficult. So I guess what it says is, so look at all the elements of M that go through U. We know we can, so this splitting is a constructive thing, so we can determine based on the proof a sub-construction of the proof that secures, that further, that covers what goes on from U down. That's what he's trying to say. That's how I read it.
But what role does it ordering property?
The plays the role that eventually you can continue indefinitely by picking one of the covering sets. So you're at a node U that's not yet in U1. So they say you're further up in the tree. You know that every sequence going through here must eventually go through one of a certain class, maybe infinitely many, but in a fundamental sequence of such that secured by the proof, and that further on is secured by some element further, but it has to eventually reach an be immediately secured. The well-ordered property comes into play by the fact that the proof is not infinite, that if you keep picking children in this proof, you will eventually get to a leaf. Right? I think that's the role it plays. Okay. So this species T is constructed by means of generating operations of the second kind. So where we have a fundamental sequence and put them together in a tree with a new node at the top. Of which each corresponds to the inversion of the continuation by a new free choice of a certain finite initial segment of choices that are uninhibited. Okay. Then to a new choice that is inhibited, okay, or terminates, there corresponds for this generating operation W, a primitive species consisting of a null element or a full element. Okay, so this thing about null elements is about just having a different way of securing things that are inhibited. And I keep suggesting that we try to ignore, we just restrict to the uninhibited elements. He has to do a little bit of extra song and dance to keep track of inhibited and uninhibited element and have a primitive null inference for the inhibited ones, I guess. Could be wrong, that's how I pass it. Okay, now, for the proof of this assertion, we denote by F sub U the species of those elements of sigma whose securability we ascertain in the course of the canonical proof K sub U. Okay, so we have the canonical proof K sub U, and this tree determines a species of elements we secure in sigma, right? And we say that a constructional underspecies, so again, that's one of the things that is pointed to by one of the generating operations for a proof or a tree, constructional underspecies. Oh, it's you. Yeah, okay. Yeah, of KV possesses the well-ordering property if every element of sigma whose securability we are certain in the course of U possesses the property of being well-ordered. Okay. We shall say that the preservation property holds for a constructional underspecies U of K sub V if in case every element of F sub V upon whose securability the proof U is based possesses the well-ordering property. Every element of F sub V whose securability is derived in the course of U likewise possesses the well-ordering property. Okay. Then as we observe the generation of K sub V, so remember, we see by means of the inductive method that for every constructional underspecies of K sub V, hence in particular for K sub V itself, the preservation property holds, but from the preservation property for K sub V, the well-ordering property immediately follows, hence for the list V itself, which he calls F sub the list. Okay. So then there is, he's not getting any easier, and I think we'll have to wait a little bit until we see the treatment in Trollsdorff and Dahlen to really grasp this part of it. But what I do want to point to right now is this footnote that comes, footnote 9, which I think people later recognize there's something wrong here. He says that one of the inferences is superfluous, so can be removed. If the securability of F sub V is ascertained in several proofs K sub V, or in several places of one and the same proof K sub V, the corresponding T are all generation equivalent as follows by virtue of the inductive method when we observe the generation of one of them. This remark incidentally is superfluous for the proof above. Okay. So there's something about whether you can make do without one of these inferences. Okay. So by now he takes it to a bit to have argued for this fact that you have this you have the proof. And let's see, what I say? Maybe some of you would like to summarize at this point. Yes, I think. I think he's argued for the securability of every element in the spread. So now comes the finitary case. So let's take a deep breath.
What does finitary mean?
Just about to say we now say that a finitary spread is a fan, and a finitary spread, so it's defined in the definitions of a few pages earlier, but it means that at every node, only finitely many children are uninhibited or allowed in the spread. So you have a bijection, a constructed bijection of a finite number. You give a number n, and you say these are the finite possibilities. Okay. That's a finitary spread, or what we today call a fan. Okay. So if M is a fan, the well-ordered species has the same content, T has the same content as a well-ordered species Q that is constructed without the use of null elements, and moreover, in a way parallel to the construction discussed above of T, namely in such a way that to each operation W used for the construction of T, there corresponds a generating operation V of the first kind, that is using just a finite list of subtrees for the construction of Q, the terms of V being similar in sequence to the species of the full elements of those terms of W that contain full elements. So what he's saying is, in this case, so the proof, the canonical proof mirrors the structure of the spread. And if the spread is finitary, so that it's a fan, we can survey each of the finite nodes that are being secured in a subproof. And we can collect those finite choices together to at the root, we have a finite list of nodes being secured that will cover the whole tree, the finitary spread. That's what he's saying here. But from this, it follows that the species of elements of Q as well as the species of full elements is finite. That's what I just said. Hence, that in particular for every natural number S, the species of the full elements of T is finite. Thus, a natural number Z can be specified such that an arbitrary element of mu1 possesses at most Z subscripts. So remember that mu1 is the bar, this detachable subset of this the lists in the spread. And in the case of a fan, we can get a number of C such that every element in mu1 has length less than C. That's what he says, that number of subscripts. Okay, that's the fan theorem. Incidentally, that's of course classically equivalent to the fact that if you have a finitely branching tree, which is infinite, then there's an infinite path, which is Koenig's lemma. And Koenig's lemma, that's from 1927. So that's basically, Brouwer had this argument already in 25 or 24. So it's one of the few cases where people agree that the intuitionistic argument came before the classical argument. Okay. Incidentally, I don't know why, but Koenig was Hungarian, just like Erdős. So the subscript, it's not an umlaut. It's two the Hungarian accent. But usually people just write, say, Koenig's lemma with an O umlaut. I don't know why, but Koenig was Hungarian. Okay, so now finally we can reap the benefits, and then we'll take a break. So now we have a natural number beta associated with an arbitrary element of M, and it's determined, completely determined by the first Z generating choices of E. So what he's saying is you have a function from a finitary spread that is a fan to the natural numbers, then you can determine a bound such that the function value is determined once you give a subsequence of length of that length, then every sequence that has that same prefix will get the same value. Okay, so that's a continuity principle for functions on a fan. Okay, and that's what he summarizes as Theorem 2. Okay, let's take a break here. Then we'll deal with how we get from here. Now this is the fan theorem. First part was the bar theorem, and we'll formalize it when we have a look at Schroeder and Van Dalen. Now I think Brouwer's statement of the fan theorem, that's much clearer than his statement of the bar theorem that was sort of inside the argument. So we'll get more details on the bar theorem once we look at Schroeder and Van Dalen. And but before that, we'll just have a look at what follows from the fan theorem, namely the uniform continuity principle. Let's take a 5-minute break.
little disconcerting having the.
But that's just yeah, we see it backwards, but
they see it forwards.
they see it forwards. Yeah.
Yeah.
I guess video apps do that to make it less
Well, I came
confusing.
Less
for-
like you're moving this way, and, then you
suddenly,
see
yeah.
yourself moving the other
Yeah.
way.
Yeah, that seems like it would be.
But the recorded video is flipped
You're
around.
on, you're on the right
Chalkboard is
side.
mirrored in
In the way in our view, but in the video itself, it's
Yeah.
correct.
Yeah. So.
Yeah, they do that because it looks like you're looking in the mirror.
Yeah.
Oh.
But then you worry if other people see it the same way, but they don't.
All over the place. And that must be the wrong building.
Now, this is just going. Try to imagine who at the
So I walked all the
time
way
that
down the hall.
consider that approved.
Went up.
You know?
Got
Yeah.
really got lost last
I
night.
like to understand.
Well, maybe we're the right direction.
And so then I realized.
That's right.
All right, I have to get there.
Rob, you're meeting with
Hopefully
your
you're
house?
Yes.
Okay, because I got
I
Jeremy's
think I'm going to
email
walk back
and
indoors.
I misread. I thought he said we'll meet at 4 after Ulrik's seminar, and then I read it again earlier, and he said 3 after Ulrik's seminar. So I don't know if that was a typo or he doesn't know when it's over.
I'm not sure I got an email.
Okay.
Yeah, because
Yeah.
Yes,
this doesn't actually count for my graduation. It took me above 80 minutes. So,
Oh, okay.
yeah, I was just like,
Right, because I'm like, wait a
also, I'm
minute.
sorry, but is it okay
Yeah.
to leave a bit like right now because of
I'll send an email.
Yeah, because I'm like, I'm trying to, is he expecting us
Yeah.
right now
See you
or?
next time.
But if you can keep me on the
Yeah.
Yeah. I look at it again, but I'm pretty sure
I do vaguely remember him saying great.
yeah, I think he thinks it ends with three. Let me check. You said gray, so I'm just gonna go there.
Yeah, I mean, I just sent an email. He hasn't answered yet, obviously. I don't think he would mind if we showed up at 4 considering that.
Oh, you let him know?
Yeah.
Okay.
If he answers my email and says, come over here now.
Okay, sure.
All right.
I'm gonna have to leave at 3:30. I just wanted to.
Okay. So let's continue with section 3 of Brouwer's paper. And finish up. We have a list and a full page left to go. We just proved Theorem 2, which was the fan theorem. So if you have a fan and a function from a fan to the natural numbers, then you can find a natural number set that completely specifies after that length of a prefix the behavior on any element of the fan. Okay. Now in the unit continuum, we determine for every natural number nu the k nu intervals ordered from left to right that partially cover the interval from 0 to 1. Then the finitary point set J formed by the nesting of intervals k, where each interval is contained in the strict sense in the preceding one, coincides with the species of the unit continuum. That is, every such nesting of intervals belongs to an x in the unit continuum, and every x in the unit continuum contains such a nesting of intervals. Okay, so what he's doing here, he's putting some restriction on of a point of the unit continuum such that he gets a finitary spread instead of just a spread. So if you just have the binary intervals, the binary fraction intervals, then there's an infinite, I mean, given a particular one and you want to pick the next one that's strictly contained in it, there are infinitely many choices you can pick. You can make them arbitrarily small, so there are infinitely many. But if you restrict to say that you go up to at most 4 times smaller, then you still get the same points, but now you have a finite amount of choice because you have to pick dyadic rationals as the endpoints, and so now you can always pick something, but you can't pick infinitely many. Okay, so he says that every the unit interval is the point set of a finitary spread. Because that's what we have to use the fan theorem. Now, in the case of a full function, f of x, a nesting of lambda intervals is associated with every nesting of intervals, and by theorem 2. So now we appeal to the fan theorem for a particular full function. So by the fan theorem, there exists for every natural number nu a natural number m sub nu, of which we may assume that it does not decrease with increasing nu, such that lambda nu is determined by the choice of the first m sub nu intervals in the input, right? So when we want to look at the nth output interval of our full function, and we say that for each I want to know the first new outputs of the function. Then so that means you get a function from so taking that index of the output sequence. That just now gives you a function from the finitary spread to natural numbers, the natural number that index that interval. So this is now something that we can apply the fan theorem to. Okay, and now we immediately conclude uniform continuity because now only a finite number L sub nu of lambda intervals can occur as lambda nu, and there exists for them a maximal width that converges to 0 as nu increases beyond all bounds. Let us denote by T nu parenthesis rho the interval that is concentric with k nu rho and whose width is 3/4 of the width of k nu rho, and that P1 and P2 be two arbitrary point cores of the unit continuum that are less than 1/4 of the width of the k nu intervals apart. So we have to maybe look up this funny less than sign, less than circle. Let's see if where was the less than circle?
456 at the bottom.
Yeah, so that's just the ordering of points in a continuum over a dense ordered set. Okay, so it really is just the order. It just reminds us that we're dealing with points in a continuum. Okay. But since we have this bound on the length of the intervals, we can determine a T nu that contains both of the point cores P1 and P2, and by means of this T nu mu nu and nesting of intervals K belonging to P1 and a nesting of intervals also that was K1. So we have first nesting is K1 mu 1 up to K nu mu nu, K nu plus 1 sigma 1, and so on. And for the other ones, it starts the same way. So the first new terms are the same, right? So, and then they might continue after that. Belonging to P2 can be determined. Now let epsilon be an arbitrary positive quantity that is positively different from 0. If we choose nu sub epsilon so great that b sub nu sub epsilon is less than epsilon, and we put a sub epsilon equal to 2 to the minus 4m nu epsilon minus 3, then according to the second paragraph of the present section, to any two elements of J for which mu1, mu2 up to mu m nu epsilon are equal, there correspond two values of the function f whose difference is less than b nu epsilon, hence less than epsilon in absolute value. According to the third paragraph of the present section, therefore, it is also the case that to any 2 point cores P1, P2 of the unit continuum that are less than a epsilon apart, there corresponds two values of the function whose difference is less than epsilon in absolute value, so that f turns out to be uniformly continuous. And we have proved theorem 3, every full function is uniformly continuous. So it's not easy reading, but we can see what goes on, right? We use the Fan theorem. So we're given epsilon. We use the Fan theorem to pick a bound on the input intervals that makes sure that that any output is that's smaller than that, maybe 4 times smaller than that, quarter smaller the output, and then it follows that if you take any two representatives of point cores P1 and P2 that are less than that apart, then because we can pick choice sequences that agree up to in the first new terms, then the function will have to agree up to epsilon on them. Right? So it's a fairly straightforward corollary of the Fan theorem, although the prose is difficult. Yeah, so that's something Steve mentioned, that how would the contemporary mathematicians have looked at this? And I can only imagine that they also found it difficult. It's not just us. So for something that aims at clarity, it falls a bit short on that goal, I think. Okay. Any questions now about the paper for now? I think we can return to the finer points of the argument for the bar theorem once we've looked at a more palatable presentation of it. Then we can see if we can make sense of that part of the bar theorem. But certainly the argument for the Fan theorem wasn't too bad, because we had those proofs, which were these constructions and these trees, and we had that if proofs were also finitary, and hence, and then that required some kind of argument about the well-founded structure of a finitely branching tree, that it had a finite number, so the converse of Koenig's lemma. So if you have a well-founded finitely branching tree, then it's finite. Right, so that's what he uses, and then we get the Fan theorem, and then we get the uniform continuity theorem. right, so let's pat ourselves a bit on the back because that was hard work. And now let's take a smooth ride for the rest of the day, going through the sections I assigned for chapter 4 of Trollstrand for Dot. So we're going to jump a little bit around in it because they discuss some of the axioms that are related to Russian constructivism and recursive mathematics in the middle, and we're just going to jump over them and return to them next week. Okay, but we start with section 2, which is about the continuity, the choice axioms, and they're very related to the discussion we just had about Brouwer's notions of the Brouwer and the Fan theorems. So let's just look at section 2.1, the axiom of countable choice. So A, C, and N. If for all n there exists an m, a, and m, then there exists a sequence alpha, such as for all n, a, n, alpha, n. Okay. So we justify this by looking at how could we come to know the premise. We must have a law that assigns to every we must have this law that assigns to every number another number, and we can just make a sequence out of those. So it's a law-like sequence. That's the output. Okay, so now comes the so we generalize it to arbitrary domain. So axiom of choice of numbers, not a big deal. Let's skip a little bit ahead. Oh yeah, there's this important comment on the bottom of the page. What happens if you try to do the general axiom of choice for any two domains? And remember here, domain is something where we give a way to generate the elements, and we give an equality relation on the elements. Right? And then what can go wrong is that even though you have a method of getting from any element of the D to an element of D prime, that may not respect the equalities. And the example here is the true statement for all reals x, there exists a number x is less than n. So the Archimedean property on the real line. And of course, it is true that for any, say, a choice sequence representing a point core, point in the real line, you can find a number that bounds it, but there's no such extensional operation. We're on page 180, 189. 189.
The reading of the existential quantifiers mean there exists a method, just technical credit. It's not stated accidentally somehow, or is it
I think
stated in words as an assumption?
We have several viewpoints. I mean, we talked a bit about it in the first meeting where you weren't here. We generally try to interpret logic intuitionistically using the proof interpretation, where we have it follows from that. But of course, we could also formalize that. If we look at a formal calculus, and we could ask whether we have the disjunction property and the existence of numbers property and so on. Okay. And we also talked about Markov's rule last time. So if you have a for all exists from numbers to numbers, then you can, and you prove it in a formal system, then you can extract a function, computable function. Okay, so we have both of these elements. We have the informal interpretation, and we have some formal some proof theory that justifies it in some sense. Okay. But in this chapter, we're adding some axioms, but we also discussed the intuitive arguments for why we would have them. The motivation for them. Yeah. But otherwise, it's a proof theoretic and we see what follows from what happens if we add this axiom. And here they're introducing a bunch of axioms that you might or might not add. Okay. Let's see. So yeah, then this motivates the presentation axiom. Let's return to that some other time. We have the axiom of dependent choice. Let's also skip that for now. Okay, and then we skip. So main thing I just wanted to make sure we understood the argument for choice, because that will come back to us when we talk about continuous choice later in the sections. So now we skip over Church's thesis, which we'll talk about next time, and realizability. Also, we'll postpone until next time. And section 4. And Markov's principle, which we postpone until next time. And then we go to section 6, which is on page 206. Okay. So here's a discussion of the flavors of choice sequences. And we already mentioned a bit about this the first meeting. So there are a variety of interpretations of any kind of process that's not necessarily predetermined by a law on algorithm. And in subsection 6.2, there he discusses some of the varieties. We can have completely lawless sequence where we never restrict to any particular process, or we could have hesitant sequences, point B, where we at some stage we might decide from now on to conform to a law, or we can have the law-like sequences. And I mentioned some other possibilities in our first meeting. You could also have, say, you decide to choose the elements by a random process or a physical process. That would be another notion of choice sequence. Right. But I think it's important to highlight this one notion, which is the lawless sequence. Sometimes we can confuse, because Trollstar has a particular axiom system for lawless sequences, and we can come back to that later. But that's just a particular subspecies of the various notions of choice sequences, which need not be lawless. Could be half lawful or random or something like that. Okay, so let's go to subsection 6.3, which is the weak continuity principle. So here we have a functional phi defined for all choice sequences. And the fact that this is everywhere defined, and then so there's an intuitive argument, because the input, a sequence of numbers or a function from n to n, it need not be a law-like function or a law-like sequence. And that means that if we have such a functional, it cannot look at an index or any finite description of the sequence. It can only look at initial segments to decide what the output should be. And that leads us to get this continuity principle. So the weak continuity or local continuity says that if you have that for all alpha there is an x, a of alpha and x, then for all alpha there is x and y, such that for all beta in the restriction of alpha to x, alpha holds of beta and y. Okay, so that's similar to the argument that Brouwer gave, that if you had a function from a spread to the numbers, then when he had a more global, but the local principle here is that, he had the local principle for the infinitary spreads as well. So for the possibly infinitary spreads, like the full bare space. So bare space is the set of all sequences here. And for all elements in bare space, you can assign a natural number such that some property holds. So you have that law that associates from an element of bare space to an element of the numbers. Then you also know for all alpha that there's a modulus of continuity for that at that alpha, right? So that's some number x, such that for any sequence that passes through that initial segment, you get the same output, or it's determined at that point. Okay. And then there's an interesting observation that if you formalize things this way, then in the disjunction form, weak choice for numbers in the disjunction form, that you actually get a refutation of law of excluded middle in the sense for all choice sequences, P of alpha or not P of alpha. And that can be refuted using the continuity principle. Right? You just assume that you specialize it to being equal to the 0 sequence, and then you get a modulus of continuity at the 0 sequence, but then you can decide after that that prefix is to start putting in deviating from the 0 sequence, and then you refute it, exclude the middle in this form. Okay. Let's. Yeah, there are many interesting things. I don't know what we want to. Let's skip the connection between weak choice and Church's thesis. But let's focus now on 6.8 on page 211, neighborhood functions and weak continuity. This is where we go from kind of local continuity to a more global continuity principle. So this is quite important. I hope it's not. Are you okay with? I'm just going through it this way because I asked you to read it, but maybe it's probably good to summarize what I think are the main points. Okay, good. So I think this is a main point. Neighborhood functions. If we have this functional phi, it seems plausible to assume that we actually know whether an initial segment suffices to compute the output there, and so that means that we get this neighborhood function. So here we're again punning the natural numbers with lists of natural numbers. So let me try to maybe unpun that and introduce some typing discipline for that. So let's get rid of our spread for now. Okay. So we have capital phi. And this is how Trollstrand van Dalen writes Baire space, and it's a functional Baire space to numbers. And then what we get is a neighborhood function little phi, and we can write like this, or as I wrote before, it's this type of lists. So you have a function from lists to, and then we actually we go one better than this saying to numbers that's encoded as the maybe monad. So 1 plus n. So something in the left. So this just means the disjoint union of a singleton with the natural numbers. And if you're in the left, it means more information is needed. And if you're on the right, it means we're done. Okay. So they code this. They use a bijection to the natural numbers where this means 0, and these are 1 plus the element here. Okay, so so what we require is phi of u equals the sum n, then for all v u a subsequence of u, extend u anyway, then phi b should get this. If at u we already have enough information to know the output of capital phi, then if you take any extension, you also have enough information and you should get the same results. Okay. That's something that we require for our neighborhood function. And we also require that for any sequence, eventually there will be enough information to give the answer. So for all alpha, there exists a u such that alpha is in u, and phi, and I guess there exists u and n, alpha is in u, and phi of u is some n. And then we just say phi alpha equals n if and only if there exists a u, alpha is in u, and little phi of u is some n. And then that's independent of which u it is. Doesn't matter which one. We know that there is, given alpha, there is some u. Make sense? I hope I did. I didn't really make. I didn't write down this definition before, but I think we can make it up. Something that makes sense. So this is a neighborhood function for a functional from bare space to the numbers. Yeah, so that's the conditions are the conditions 1 and 2 in the text. I just swapped them, give them in opposite order. Okay, so then there's the important class K0 of neighborhood functions, which are now these functions that have these properties, and with the output defined as the way I just gave it. Then global continuity, Cn, says, if you know for all alpha there exists an x, then there exists a gamma, a neighborhood function, such that for all alpha, a of alpha, gamma alpha. Right? So that means that for every, you get it by using the kind of axiom of choice in the way we talked about you should be able to do. If you have this for all alpha there exists x, then you have such a capital phi, and if you have such a capital phi, you know a neighborhood function, little phi, in or here called gamma. Okay. Okay, so that's the continuity principle. There's a good picture of on page 213 of the neighborhood function associated with the functional take alpha and evaluate alpha at 0, and then evaluate alpha at the output of alpha of 0. So that should help explain what that looks like. Then proposition 610 is an equivalent formulation of continuity. You don't have to use that at the moment. It might be worth noting 612, the neighborhood function principle, NFP. If for all alpha there exists an x such that a property holds of a prefix of the prefix of alpha at x, then there is a neighborhood function such that for all alpha a holds at the prefix given by gamma of alpha. Okay, so if you have weak choice and the neighborhood function principle, then you get continuity and vice versa. Okay, that's the case. So it's a special case, but with a bit more, just a bit of choice, you get the full case. Then you can generalize this. These discussions were about the particular spread, the universal spread that we call bare space. You could also formulate them for an arbitrary spread T, and then we get the obvious restrictions. But let's skip to section 615, function continuity. So suppose for every alpha there is a beta now in bare space, such that A of alpha beta. Then there is a continuous functional from bare space to bare space, such that for all alpha that. Okay, this is the obvious choice principle. Okay, so let's see if we can express this in terms of neighborhood functions. And here comes, this is a bit of classical mathematical logic, gamma applied to alpha. And we say that is beta if you can compute beta of n by taking gamma at the singleton list n applied to alpha. So it's a way of, suppose you have a function of, say, psi from n to the n to n to the n, and then you curry it to say it's similar to having a function from that takes a number and an element of bare space and gives you a number. And then you can also code this up using, say, the first argument of the list here becomes this index here. And you could probably write a nice functional program that had a bit better typing than here, and then explain how to do this application so you code this up with a gamma, and then you have this gamma applied to alpha. Okay, so that was section 6. Now we are at section 7, the Fan theorem. So here the order is reversed. So in the Brouwer's article, there was some discussion about the bar theorem, and then the Fan theorem was derived. And here they discuss the Fan theorem first. And they just introduce the Decidable Fan theorem, that if you have a affinitary spread that is a fan, then if you have a decidable property, and you know that every element of the fan goes through that decidable property, then there exists a uniform bound such that for any element of the fan, there is some sequence of length at most c that goes through that property, the bar, so to speak. Okay. And then what I mentioned before, we may think of the Decidable Fan theorem as an intuitionistic version of Koenig's lemma. Of course, classically, they're equivalent. Now, what about the full fan principle? This just says that for any property, not necessarily decidable anymore, if any sequence goes through the bar, then there's a uniform bound such that any element goes through the bar at most that length. And again, there's a topological argument. So then there's some meta mathematics here, or the relationship between them. If you have the neighborhood function principle, then you can derive the general fan theorem from the decidable fan theorem. And I guess we should know the proof, but I'm going to skip it for now. You can also derive the fan theorem and the decidable fan theorem from the case of the binary tree. Okay, so then it really looks like Week's Koenig's lemma, where Week's Koenig's lemma is about the full binary tree. Okay. We skip the connections to Church's thesis and extended Church's thesis at the moment, but for now, let's just note that fan theorem is incompatible with Church's thesis. We'll talk about why next time. Then we have the intuitive motivation using this bar picture. We already talked about that. Okay, so let's go on to section 8, and then we'll finish up for today. Bar induction and generalized inductive definitions. So talk about regular trees. So trees that either have a full omega branching or a leaf. Okay, and define well-foundedness and how can we inductively generate the regular well-founded trees. Well, there are two inductive clauses. Every singleton tree is regular and well-founded, and if you have a fundamental sequence of such, you can combine them into a new regular well-founded trees. Okay, so that's the inductive notion of trees, called IT in script in the book. And we can also generate them based on some neighborhood functions. So this is I think an interesting part is section 8.3. So we inductively generate a class of functions on that corresponds to these regular trees. So then we introduce another class K, and it's then argued here in the book that Brouwer's bar theorem amounts to the assumption that K naught, which we defined earlier, is equal to K. And what is K? K is an inductively defined class of functions. And we say there are three clauses on page 226 that the function that immediately outputs sum x, that means that lambda n x plus 1, that's what we coded as sum x. Those functions are in K. And if you take any function which says no at the root, so alpha of the root is none, and if for all x lambda n return alpha at take first x and then extend it with n, that thing. I think there must be a typo on their section K2. What is meant is you can gather up if you have a function that lists a number of functions so that you give the output for the following things, and you can combine them into one function that says no at the root and then uses that sequence of functions at the immediate descendants. Right, and then okay, so that's this element K. Maybe it's better to look at K star. If you have, yeah, so the notation is a little bit weird, or maybe I don't just, maybe I didn't spend enough time preparing it, but lambda x1 is in k star, and if for all x, gamma x is in k star, then gamma is in k star, where gamma is this thing that says no at the root and defers to gamma x applied to n if you have a sequence that starts with x. Okay, so it's a way of coding up a sequence of functionals and as one function, sequence of functions, one function. So this is the inductive presentation of K naught. So okay, let's read from section 8.8. Brouwer's bar theorem amounts to the assumption that K naught equals K. The effect of equating these is to equate two notions of well-foundedness for countably branching trees. So we generalize the Fan theorem in the same way that the Fan theorem generalized two ways of equating well-foundedness for finitely branching trees. This identification is plausible only if the range of the function quantifier over the bare space over spreads is taken to contain all choice sequences. If we have too much information about an arbitrary sequence, then this is no longer plausible. Okay. Maybe we'll return to this at a later time. Okay, so let's go to the actual axiom. That's I think for now the important part. How do we then formalize decidable bar induction? It's section 811 on page 229. So you have some predicates P and Q, and Q is your goal predicate, so to speak, and P is your bar. So what are the premises? The premises are for all alpha there exists an X such that the X segment of alpha is in the bar P. And the bar has to be decidable for all n, Pn or not Pn. And everything in the bar has to satisfy the goal predicate. So for all n, Pn implies Qn. Then, and there's one more premise, for all n, every one element extension of the sequence represented by n. So if your goal predicate is upwards closed, so if it's satisfied for all all children, then it's satisfied at a node. Then you can conclude that your goal predicate is satisfied at the root. So that's a way of doing induction over trees. So you know you have a bar in your tree, and you know that your goal holds at the bar, and then you do upward deductions until you get to the root. Okay, and then there's a more general version, the monotone bar induction theorem or axiom, where we just require the bar to be monotone but not necessarily decidable. But they are equivalent under continuity principle. And let's let me skip ahead to because we haven't talked much about these formal systems, but we have talked about Brouwer's argument. So let's skip ahead to 8.18, where we now get Troelstra and Van Dalen's discussion of Brouwer's argument. So let's try to see if that helps us a bit. So have notion of a bar, and so the basic assumption underlying Brouwer's proof is that from any proof that the root is barred, one can extract, a node is barred if everything going through that node eventually reaches the bar, okay? Or has a prefix going through the bar. So such a proof should be analyzed into a proof made out of three types of inference. An immediate inference that a node is barred, or a downwards inference saying that if you have a list, then you chop off, and that's barred, and you chop off an element, then you get fewer sequences going through there. So then that's barred. And if n is barred, then so that was the upwards. The downwards, I guess we call that upwards because we're drawing trees downwards and they're drawing trees upwards. So that's a little bit confusing. So for that was actually an upwards inference for all x. We call it upwards. They call it downwards. For all x, the extension of n with x is barred, then n is barred. And then downwards is the one. If n is barred, then n you have extension, because now we have a smaller set of sequences going through. Okay. Yes, those were traditional calls, eta, wow, and rho. And here we are. Okay, so the obsolete Greek letter wow. So under suitable assumptions on the bar, the single premise inferences are eliminable. This is the case for monotone and for decidable bars, but there's an example shows that they're not eliminable for an arbitrary bar. And then so there's this discussion about how you can get a counterexample to show that you really need to have those inferences there as well. Does that help? So to sum up, we had these arguments for bar induction for the Fan theorem. We saw that the Fan theorem implied uniform continuity, and we saw that the motivation for having these spreads was somehow to get a full continuum where you not just have the law-like points, but you can have much more. And next time we'll see a radically different conception of real computation in real numbers, and what kind of things you're allowed to do with them when we talk about the Russian constructivists. So for here, let me just finish with this. So we saw that for functionals on bare space for Brouwer, they had to act on finite information. So in a sense, it's a prefiguring of Turing's notion of an oracle, right? You can make finitely many requests to the oracle, and then you have to give your answer. But for the Russians, they use computation on indices of sequences instead. So you give a program code, and you're allowed to inspect that program code for the entire sequence. So that's the two different ways of computing on functions that we have from Turing. We have the oracle computation and we have index computation. And today, for Brouwer, we saw that his notion of functionals on bare space are like the oracle computations. And then for the Russians, we'll see they come after Turing, and they take everything to be index computing. And we'll see that gives a very different picture of the continuum. Okay, that's it for today. I'm going to stop the stream. See you next time.